Right, let me just move my windows around a bit.
Should we give Dara the host, or
I give the host to the
yes,
yeah.
you might wanna.
Yeah, she is
Okay.
also
So I can share my screen. Yingtong, shall I just share the screen?
yeah, you
Yeah,
can do.
공유.
Is this meeting recorded?
Yes, it is recorded currently. Yeah.
Okay, cool.
Is that working?
All right. Yeah, I see that.
Yeah, we can see.
Okay, cool.
Okay.
Do you want to start, Yingtong?
Yeah, should we start now, or I guess people can just join when they join, right?
Oh,
Yes,
yeah,
since the
it might
time
be
is
worth
too late,
waiting.
maybe it'd be better to just start this presentation that way.
Okay, so hello ZK Seoul, and thank you for having us. We're Dara and Yingtong from the Electric Coin Company, and we're gonna talk about Halo2. So the outline of our presentation is on the next slide. So what we're gonna do is walk through the high-level protocol first, and then after that we'll go into details of the math and the implementation. So yeah, Halo 2. Some of us may have heard of Halo already. On the next slide. So Halo 2 is basically Halo, but with a more efficient arithmetization. So instead of using Sonic, Halo 2 uses Plonk, as you'll see on the next slide. But from that point on, the commitment and accumulation schemes are as before. So those have not changed. Yeah. So now we're gonna walk you through this diagram step by step. Step 1, arithmetization, Plonk. So yeah, what arithmetization is basically a way to express a machine's computation in a form that we can do probabilistic algebraic checks on. And it's something that every proof system needs. Some of us may be familiar with R1CS. It's the rank 1 constraint system, where each constraint is of the form A times B equals C. So in Plonk, we have a more general constraint or more general polynomial rule that you see at the bottom of the screen. And actually the best way to explain this rule is to just use it. So we're going to an example on the next slide. Okay, so let's say we want to an addition gate. We want to enforce A0 plus B0 equals C0. And how we would do that in Plonk is, first of all, we'll set our variable, so XA, XB, and XC columns on the left. 3 columns. Set our input, our left and right inputs, as well as our output. So we'll set our left input to A0, our right input to B0, and they should add up to our output C0. And to sort of activate these variable gates, we'll also set the selector gates. So these are the Q columns the selector wires, we'll set them to 1. So we set QL to 1, so the left wire is activated. QR is also activated. And we set QO, Q output, to -1, so that in the end, the equation comes out to A0 plus B0 equals C0. And actually, this equation is pretty general. So you see, you can do a multiplication gate if you want. You can enforce some public input if you want. And you can even do a Boolean check that x squared equals x. So x is either 0 or 1. And by the way, stop me if you have questions at any point. Right, and now you can see we can go one further and find our own polynomial rule. So we don't have to stick to standard Planck. Over here, we have a running product gate. And you see what this gate is doing is it's checking a value from the previous row, ci minus 1. And it's taking that and putting it into the current row. And we can product gate. You can compose gates quite easily. The running product gate has a QP selector that's wrapping it. So we could easily add that into standard Planck and turn it off and on by changing the value of QP. So yeah, that's Planck. And the point is that then be expressed as polynomials. Right, so something you notice in the running product example, and in fact in the running product example is we refer to the previous row, right? And so this hints that we need a capability to copy over value previous rows. This example, in this toy circuit diagram, one output circuit to be left in of the output of first gate to the left of the gate. And in other words,
I've lost Yingtong's
we
sound.
want
Is that okay for everyone else?
wire together.
I think it's lagging a little bit. I'm sorry, Yingtong, can you like repeat what you have done for like 20 or 30 seconds again? Is she offline?
She might not be able to hear us. I can't actually see the Zoom window because I'm screen sharing.
Hi.
Oh.
Can you hear?
Hello.
We can, but it's very laggy. Could there be anything else using your internet bandwidth?
Okay. No. I have slow internet in Singapore. But okay.
It seems to be better now.
With a lag. Okay. So, like I was saying, we want to be able to copy values from one row to another. And in this way, we wire together the constraints, meaning independent constraints, is through a permutation check. So on the next slide, you can see that, yes, on the next slide, you can see effectively what we're doing when we're copying value. It was already be sigma v, which is the set of values where we have swapped A1 and C0. So one is really worth the same. Then shouldn't be able to tell a difference between V and sigma V. And in other words, the permutation sigma equals change this set of values. So, and we can see even a more complicated example on the next slide, where we can have more than one copy constraint, and we can cite longer. Yeah. Okay. So this copy constraint is turned into a polynomial is on the next slide. So it's through something called a grand product. So over here, Plonk actually works over a multiplicative subgroup, and that just makes life easier. What this subgroup is a group that is generated by some primitive root of unity omega. And basic elements of the group are just the increasing powers of omega. And this group is such that at some point, it actually wraps around. So every omega n plus k is equal again to omega k. So omega n would be equal to omega 0, which is 1. So we're in this subgroup. We're evaluating f over 1 omega all the way to omega n minus 1. And the prover wants to prove that some f omega to the I is equal to the permuted omega. So f omega to the sigma I. Yeah, and so this is how we're going to arithmetize the permutation check. So we define two permutation polynomials. So the first is f prime, which corresponds to the identity permutation FID. And the second is g prime, which corresponds to the permutation polynomial f sigma. And you can see we've added in some random betas and gammas, basically so that the prover can't cleverly fake these values without having them still be equal. And what we do with f prime and g prime is we evaluate them on the powers of omega, and we compute their the fraction of f prime omega over g prime omega over all the powers of omega. And in fact, what we do is we take this fraction and we accumulate the product of it into a grand product zx. So you see over here, we want the first term of zx to be 1. So, well, actually, let me explain the second relation first. So we want some things to be true about zx, right? So we want, looking at the running product, we want zx to be well constructed. So if you recall, z is the running product of f over g. And so the next term in z is just the previous term, z omega I, times f prime omega I over g prime omega I. And if we rearrange that, then we get the second relation, zx f prime x equals g prime x z omega dot x. So yeah, this is something clever that Plonk does, because basically being in a multiplicative subgroup, it allows you to perform a right shift on z. So z omega x is the evaluation of zx on the next point. And in this way, we can check that the running product holds at each subsequent point. So all that's left now is then to check that at the first point, we're starting off at 1 as we expect. And if these two conditions hold true, then we are convinced that then we are convinced that the permutation is equal to the original polynomial. Yeah, so that was how Planck converts a series of constraints, so and as well as permutation checks polynomials. So we've successfully done our step, and now we're left with a bunch of polynomials. The next step is to commit to these polynomials. And by the way, I'm gonna stop if people have any questions. And if not, oh, we have a address as well.
I just have a tiny little question.
That we, yeah.
So Planck is arithmetizing the circuit in a more general way, right? Right. It's a little bit different from rank 1 constraint system, which means it also increases the circuit when there's a plus operation, right? Is that correct?
It can be. So if you just translate an R1CS circuit naively into Planck, then yes, you would have a row.
So is does it increase the circuit a lot? Is it trivial or is it conspicuous?
So in practice, you can almost always get a smaller number of rows than the R1CS constraints, because you can use custom gates, which will that running product example was a custom gate, and you can usually fold the additions into what else is happening on a row. So for example, suppose that you want to decompose a binary value into its bits, which is something you do very commonly. And in R1CS, you have to have a separate Boolean constraint for each bit. So in Planck, you will be able to do that simultaneously with whatever you want to do with the bits. So in practice, there can be quite a big advantage to Planck. So you don't get this naive blow up with the number of additions for practical circuits.
Okay. Thank you.
Cool.
Should we carry on with the commitment scheme?
Yes.
Okay.
So yeah, now we have a bunch of polynomials, and what we want as the prover is to convince the verifier that we know these polynomials which satisfy the desired relation. So to do this, we're going to use the inner product argument. Now, naively, if we wanted to convince the verifier that we knew these polynomials, we could just literally send over some shifted version of the polynomials. But that would be very expensive in terms of communication cost. It would be sending 2 n scalars for let's say for vectors a and b of each of length n. And over here, the vectors contain the coefficients of our polynomials. So the inner product argument's purpose is to reduce communication cost. And in fact, it reduces it to log n. And this was originally from Bootle et al. In 2016. And what we've done in Halo is by the inner product argument. So we're going to go straight to that on the next slide. So, right. In Halo, here's our problem setup. Okay, we have 2 vectors a and b, each of length n. But actually, a is the vector that we're committing to, and b is simply a fixed vector. So this is a publicly known vector, and it's just the increasing powers of some chosen evaluation point x. So yeah, we have a and b. And what we want to prove to the verifier is 2 things. Is that first of all, the vector a evaluates to a certain value v at the point x. So in other words, the inner product of a and b equals v. And secondly, we want to prove that the inner product of A and G, or we want to prove that there's some commitment P that commits to the vector A. So P over here is a Pedersen commitment. It's the inner product of A with some vector of random plus some shift by some other randomness, basically. So yeah, we do want to convince the verifier of these two relations.
We're losing your audio, I think, Yingtong. Can you hear us?
I can
I
hear
think we lost her again. Oh,
you. I can hear you. Can you hear me?
Yes. Okay, we can hear you now.
Oh, cool. Yes. I apologize for my internet. But
Not to worry.
okay, so where were we? If we go back to the previous slide, so basically we have PK that, oh, on the previous slide, yeah, we have PK that is a linear combination of these two relations that we're interested in proving. Yep. So that's product argument. So we're going to prove that we satisfy PK is we're gonna move through K rounds, and at first it might seem like you don't know where we're going, but it will become clear. We're just gonna do the same thing every round for K rounds. Okay, and remember our objective is to reduce the communication cost of this inner product argument. So at the kth round, what we're gonna do is we're gonna split our vectors into half. So we split A into a low and high half, same with B, and same with G. And once we're done with that, we get some random challenge UK. And we basically multiply the halves by different powers of UK in order to keep the halves linearly independent. So the effect of this is we're left with compressed versions of our vectors, so of half the length. If you look at AK minus 1, it has length n over 2 right now because it's the sum of A low times UK plus A high times UK inverse, right? So with these compressed vectors, what we can now do is write an equation PK minus 1 in terms of the compressed vectors. And the form of PK minus 1 is going to be similar, it's the same form as PK. But if we look at PK minus 1 more closely on the next slide, what we'll see is PK minus 1. Yeah, let's look at it more closely. We can express it actually in terms of our original vectors. So yeah, in terms of yeah, so this is just me writing out explicitly what PK minus 1 is. Yeah, and then we can go, we can basically group the terms in PK minus 1 by their factors. So if you look at the equation at the bottom of the page, right, the first column, these are the terms with no factor in front of them. And the second column, these are the terms with a UK squared in front. And the last column is that has a factor of UK to the minus 2, right? And what's interesting about these columns is that the first column it's actually just pk. It's our original pk, right? It's ag plus bgu. That's pk. But the second and third columns, they're quite different beasts because they actually contain cross terms. So you see, we're multiplying, we're taking the inner product of a low and g high from different hops, and a low and b high. And so we can call these cross terms LK and RK. And for every round, we're actually going to get two cross terms like these. And these are scalars, by the way, they're inner products. So yes, so that was round K. And like I said, we're going to progress through to round K minus 1 in a very similar fashion. So we'll see on the next slide that,
did I make a mistake by changing this to the bracket notation if LK is a scalar? I thought LK was a point.
it's the inner product of A low and B high.
So inner product of A low and G high is a point because G.
Okay.
And then these.
Yeah, I think
these are
you're
scalars, but then
right.
you're multiplying them by U, so that's a point.
It's a point.
Yeah. Okay. So we can go to the next slide.
Okay. Cool. Okay, thanks for that correction. Yeah. The next slide is just me making it explicit that P1 is just our original P plus these two cross terms, and we're now involving these random challenges from round K. Yeah. So now let's really go to round K minus in the next slide. And we'll see in round K minus 1, what we're doing is, again, we're bisecting our vectors. So yeah, we take AK minus 1 and we cut it in half again, and we get low and high. Same for B. And then we get a compressed PK minus 2 in terms of these bisected vectors. And then once again, we get the cross terms. We see that PK minus 2 is PK plus the cross terms from round K plus our new cross terms from round K minus 1. So we actually are picking up cross terms from the previous round. Yeah. And in this manner, we're going to move through to round K minus 2, and then we're going to move all the way to round 1. And by the way, K over here is log n. I don't think I actually said that before. So yeah, it's the number of times you can cut a vector of length n in half, right? So you've cut it in half K times, and by the time we're at round 1, your vector is reduced to a single element, A B 0. And you've also accumulated items per round. Yeah. So this is what we're left with. And so now what the prover has to do is, right, like I said, we're left with these single element vectors. And we also notice on the next slide that P0 like we observed from previous one, that's all the cross from the all K rounds. So now what the prover has to do is to send these two K and the prover A0, our final A0. And we don't have to send our 0 and G0 because we already know these are public, right? So that's why on the next slide, you can see that the communication complexity of our call is okay. It's great. And now, so the prover sends over these terms. On the verifier side, here's what happened. So on next slide, the verifier has to compute B0 and G0 since these were not sent over by the prover. Oh, is my internet lagging? Oh, okay. I see the next slide
I think
now.
it's okay.
It is? Okay, good. Yeah, so the verifier side now. So we do need to compute G0 and B0 ourselves. And how we're gonna do this is we need all the random challenges, because those were used in the inner product argument to bisect G and B, right? So on the next slide, you can see that we can arrange these random challenges in a binary counting structure into this vector S. So S, so you can see in the first column, the U1s, they alternate between the inverse U1 inverse and U1, and the binary structure arises from the fact that we dissect in every round. Yeah. So by the time we get to U1, it's only like a single. So with this, so we have this S vector that contains our challenges, and the verifier can use it to compute G0 and B0. And in fact, on the next slide, we can see a further optimization for B0. So we can exploit the fact that B is a highly structured vector, right? B is just the increasing powers of the same value X. And so B equals the inner product of SB is basically equivalent to evaluating some polynomial G with K terms on the value X, and X is like I said, X is B is just increasing powers of X. So in short, B0 in just okay time. Yeah, which is good. But this doesn't solve our computation of G0. So if you recall G0, if you recall G, the vector is a regular element, and it doesn't have a structure like B. So there's no way around it. What the verifier has to do is take the inner product of S and G, which are both length n vectors. So this is a linear time computation, which, so yeah, this is the most expensive part of our inner product argument. And in fact, this is the part that we're going to procrastinate on. And on the next slide, you'll see that this computation SG is what we're going to delegate to the accumulation scheme. Yeah. So basically, instead of actually performing this linear time computation at the end of our inner product argument across many proof instances and it only once at the end of a batch of proofs.
Okay.
So how we
I think this is the point.
Which Dara will explain.
Yes, I think this is the point where you hand off to me. Okay, so first of all, let's explain the setting that we're in. The goal of our proof system is to provide sort of incrementally verifiable computation. So the idea is that we have a big computation that we want to split into lots of smaller computations. So we have a base step and we have an inductive step. We can generalize this to arbitrary graphs of computation rather than a linear one, but let's stick with the linear for the time being. And we want to be able to represent the computation so far with a short proof, and then validate that proof, and that will convince us that, will convince the verifier that all of the previous steps were correct. And we want to be able to extend that computation just knowing the proof and the new step. So if we have a fully succinct proof system, so that's a proof system that has sublinear proof size and also can verify those proofs in sublinear time, then there's a paper that proves this. There will be some circuit size at which the system can verify one of its own proofs. So that allows us to construct this incremental computation. But as you saw from Yingtong's part of the presentation, the proof system we have using the inner product argument doesn't have that property. It has sublinear proof size, but we have a step of the verification that takes linear time. And the motivation for using this proof system is that it doesn't have a trusted setup. So we could use something like Grot16 or Planck with a trusted setup, and that would work, but we want to be able to do it without that. So the main observation in Halo is that you don't necessarily need the sublinear verification, provided that you can sort of compress two proof states. So you have two of these linear time verifications and you can compress them into one. You can keep doing that in each step of the incremental computation. So there's a, excuse me. So we published the Halo paper about this, and then later there was another paper that formalized it using the idea of an accumulation scheme. So that's this BCMS 2020 paper. So you have some proof system which has a step called the decider, which can be expensive, but you can represent the proof state using this accumulator, which in our inner product-based scheme is this value G, and the challenge is U1 to UK. And then in each step of the accumulation, you have a logarithmic time check, which is just checking the opening of G. And you replace the accumulator with a fresh instance. You have a different G and different challenges. And then at the end, so at the end of the whole computation, you can check using the linear time verifier. So you can think of, for example, a blockchain. Suppose that you've been offline for a long time. You want to be able to catch up to the blockchain and validate all of the transactions and blocks that have happened while you were away. You can potentially do that with a single proof. There's a lot of engineering work to make that work. Okay. So there are some complications to doing this in practice. So this diagram here sort of shows schematically the basic idea of an accumulation scheme. So in each step you have a circuit, and part of that circuit checks the previous accumulator and produces a new accumulator. So that's the values G and the challenge is U. And it also produces some of the proof, some short proof pi that we can check. And then these ovals at the bottom are what you would input to the decider at the end. But that's a kind of idealized view, because this would work if you only had a single field in which you're computing everything. But in practice, we're going to have two fields: the field over which the proof system is defined, so where we're doing the one which makes it efficient to do our group arithmetic, and then the field that is efficient in the circuit, and those are different. So doing arithmetic in the circuit in the wrong field, you pay a penalty of about 100 times. I'll explain exactly why that is later. But how can we solve this problem? So we basically have two proof systems, one over a field FP, in purple in this diagram, and one over FQ, which is in orange. And we alternate between the two proof systems. So we have two accumulators, and it's like an interactive protocol between the proof systems. So we, if we have a proof that would be hard to check in this field, we send it over to the proof system on the other field. And then at the end, you check both accumulators on the final proof. But even this is a little bit of an oversimplification, because in practice, our proof consists of elements from both fields. So what we do is we send over the parts of the proof that are easy to check in the other field to the other proof system, and we keep the ones that are easy to check in our own field for the next step that we're doing in the same field. And then at the end, we end up with two accumulators that we need to check, two of these deferred values, and then the final proof. Okay, so this was the case where we're just doing incremental computation in a linear series of steps. You can generalize it to a graph of proofs. So here, for example, this proof on the middle left depends on the proofs on the top left and top middle, and so on. So the proof at the bottom depends indirectly on everything else. So to make this work with this sort of bouncing between two fields, we might have to add dummy proofs into the graph. So here we've added this purple proof so that the fields alternate on every path to the root. And then if we add the deferreds into this picture, each of them bypasses one proof. So this is all we need to check. There's another option that we could do. So we could keep all of the proofs in our original graph in one field and just add these wrapper proofs in the other field. And that might be more convenient for some protocols. And there it is with adding the deferreds. It looks complicated, but in practice, it's not too hard to implement. Okay, so I'll stop there and see whether anyone has any questions.
The truth is, I really didn't understand what is going on right now with the purple proof. So you said there are two fields alternatively like pinging-ponging the proofs from one to the other, right?
Yep. So let's go back
Yes.
to this diagram.
Yes,
Go on.
this is what we're looking at. But you mentioned the purple proofs are also like skipping the other fields and the defer.
Yeah. So if you look at these, the arrows that are labeled deferred here.
Yes.
Okay. So they're in the field that we're going to be able to check efficiently in the same circuit. So we want to delay that to by 2 steps effectively.
So we have to check the alternative fields and also the same field going on through the next circuit at the same time.
Yeah. So the proof state at any point is all the arrows going out from a given circuit. So
yes,
the proof state after this first step consists of the accumulator, 1 deferred, and 1 proof for the other proof system. Oh, that is easy to check in the other proof system.
Yes. Thank you. I think I understand it now.
Okay, cool. And that's what these. This is showing basically the same thing.
Yes,
in a
it's the
different
same
form.
thing as before.
The dotted arrows are the deferreds here. Okay, cool. So what we want to do now, up to now, we've just been talking about abstract groups and fields without saying what they are. Well, our fields have been over a prime. That's all we've specified so far. But we actually want to implement them using elliptic curves because that's really well understood cryptography, and we know how to implement elliptic curves efficiently. So what is an elliptic curve? It's a group of points. So each of these coordinates is in our field FP. It turns out that for implementation in a circuit, it's easiest to use this affine form. Often when we're implementing elliptic curve cryptography outside a circuit, we use something called projective form to avoid inversions, but that doesn't turn out to be efficient in a circuit. And these coordinates satisfy some equation, and we also add a pointer to infinity to act as the group identity. Okay, so a bit of notation here. If we're defining a curve over FP and it has order Q, then we'll write that as EP arrow Q. So this is a group of points, so we can add them, we can multiply them by a scalar, and the scalar is going to be in FQ. And this proof system using this curve is going to efficiently support circuits that can do arithmetic over FQ. So we define a 2-cycle of elliptic curves as this per EP arrow Q and EQ arrow P. So that's what allows us to do the bouncing between proof systems that we talked about earlier. And so if we tried to, so suppose that we tried to get away with just 1 curve and tried to simulate this arithmetic in the other field. So in a proof system based on R1CS or Sonic, that would give an overhead for the arithmetic of about 1,000 times. So it wouldn't be practical at all. In Plonk, it's a little bit better because you can use lookups. We'll explain how later, but it would still be about 10 to 100 times overhead. So it's really important to use this cycles of curve trick. Okay, so we've said before that we use 2 instances of the proof system, but how do we construct this cycle of curves? So this is the cycle that we give in the Halo paper. It's called Tweedledum and Tweedledee. We use Alice in Wonderland references because Lewis Carroll wrote Hunting of the Snark, so it's kind of a pun. And if you look at the primes here, they're very close to a power of 2, and they have, that's for efficient arithmetic, and they have these zeros at the end. And what that means is that we have the multiplicative subgroups that we were talking about earlier. So that, remember, the powers of omega up to omega to the n equals 1. So that choosing primes with this structure gives us that subgroup. They both have 126-bit security. So typically the security level of an elliptic curve will be half the order. And here we've got prime order, so that's roughly 2 to the 254. So half that. And they're not pairing friendly curves because we don't need pairings for this proof system. And we also choose them so that these values p-1 and q-1 are relatively prime to 5, and that will allow us to do efficient hashing in the circuit. We can use algebraic hashes like Rescue and Poseidon in the circuit. Okay, so how did we find these curves? So the problem that we need to solve is the order of an elliptic curve over fp is in this range. So the size of the range is basically proportional to the square root of p. So for the Tweedle curves, that's a 2 to the 129 range. And basically, if we choose a random curve over this field, then it will have this distribution of possible orders within the range. So it could be anywhere, basically. And so let's say that our curve over fp has order n, and that's a prime. So we construct a curve over fq, which has order r, then it could be anywhere in that range. So it's very unlikely that r equals p. So how do we solve this problem? This is sort of just showing that pictorially. You start with the curve over fp, go to q, back to r, and these could be anywhere in the range, so it's unlikely that they're the same. So what if instead we could restrict the possible orders to a small number of possibilities, so that we were guaranteed that that one of them was the prime that we started with. So in this case, we have 6 possible orders for the curve over fp, and for each of those we have 6 possible orders for the curve over fq, and one of them is p. So that would be nice. How do we construct that? So, and there's a pure math paper which by Catherine Stang and Joe Silverman, where they noticed that this subset of curves, this particular kind of curve called a complex multiplication curve, have this property. So I'm going to try to explain what CM curves are, so just to give some intuition without being completely precise. So first we need to explain the concept of an endomorphism. So it's kind of a function that preserves the group structure from the curve group to itself. So it preserves the identity and it's homomorphic. So an example of that is scalar multiplication by some constant. And then you can consider the endomorphism ring, which is the ring of all possible endomorphisms for a given curve. And this is a ring because you can compose the endomorphisms as functions, you can add them, and there's an identity, so it forms a ring. So if we consider, we said that scalar multiplication by a constant was an example of an endomorphism. We can think of it the other way around. You can think of any possible endomorphism as being a generalization of a scalar. Are you still with me so far? Any questions?
Yep.
Okay. So if we have an ordinary non-supersingular elliptic curve over a finite field, then it turns out that all of the endomorphisms are just scalar multiplications. But suppose that we take the elliptic curve with coordinates in the complex numbers. So this is effectively reducing the curve over FP is reducing these coordinates mod P. And then what complex multiplication is that you can scalar multiply points on this curve by complex numbers instead of integers. So let's give an example of that. We have this curve y squared equals x cubed plus ax for some a. And we're going to define how to scalar multiply by I, so the square root of -1. So just I as it normally is for complex numbers. So we define it like this. So multiplying by -1 would be just x comma minus y. Multiplying by I is this. So let's just check that this definition works. If you scalar multiply by I squared, well, by definition, that's scalar multiplying by -1. So that gives you x minus y. But if we apply this map twice, we also get x minus y. So that works. The definition works. So these numbers that we're scalar multiplying by, they're not arbitrary complex numbers. They're numbers in a lattice. So I'll show you what that looks like on the next slide. So this example, the middle example here with the square grid is the one that we showed on the previous slide. So the possible scalars are on this complex grid. And another possibility is this sort of hexagonal grid or triangular grid. Okay, so what an elliptic curve with complex multiplication is, the elliptic curve over the complex numbers, it's the case where this grid has more than one dimension. Okay. Oh, and by the way, some really commonly used curves like SECP256K1, which is used in Bitcoin, is exactly this kind of curve. It's called the J equals 0 case. Okay, so these lattices, they form a ring, and we can consider the units of that ring, so the elements that have a multiplicative inverse. So for example, this point at 1, 0 here, its inverse is itself. So it's also in the lattice. So the points for which this is the case, they form as they fall on the unit circle here. And if we count the number of those, then that corresponds to the number of possible orders of our curve as we vary the curve coefficients. So in this example, for example, that's the equation is y squared equals x cubed plus b. So as we vary b, we get 6 possibilities for the curve order. And actually, these also correspond to sort of shortcut ways of doing scalar multiplication for particular scalars. So we're going to use that for optimization later. So if we're choosing CM curves, they're a very particular kind of curve. So we might be worried that they might be less secure. So even though they're a small fraction of all curves, there's no reason to believe that they're weaker. And as I said, Bitcoin's SECP256K1 is an example of a CM curve, and there are sort of billions of dollars riding on its security. So it's quite a well-studied problem, the security of these curves. Okay, so the point of this is to construct curves that can only have a small number of possible orders, and that have efficient endomorphisms that we can use to speed things up. And also, there's something called the norm equation, which relates the field of definition, so P here, with the order Q, and that allows us to construct cycles. So, so this is the norm equation. P is the size of the field we're defining the curve over, and all of these are integers. So it's an equation in the integers. So this basically allows you to choose these values V and T so that we have a multiplicative subgroup of the right size. I'm not going to go through the details because we've got limited time, but basically, okay, this is the diagram we saw before, where we have one of the possible orders of FQ going back to P. And we can prove, it's a fairly simple proof. Again, I'm not going to go through the details, but the point is that it fits on a single slide. The proof that you can form cycles using these curves. So the other reason for doing this in this way is that we need these multiplicative subgroups, which we used in Plonk, and that means that we need the primes P and Q to be congruent to 1 modulo 2 to the C. And C here defines how big our so the size of circuit that can be supported. So for Tweedle, C is 33 or 34, so we can support fairly large circuits. Okay. So here we're going to choose VP and TP in this way, and then it's guaranteed that the curves we find will have this two-adicity property. Okay, so a recap of where we've got so far. So Yingtong described how Halo2 was constructed from Plonk. She described the inner product argument. We used that in an accumulation scheme. We showed how to construct cycles of curves. We showed what complex multiplication is. We sort of described endomorphisms. Okay, so the next part of the talk is on circuit optimization. Are there any questions about where we got to so far? Okay, I will just carry on then. So in practice, our circuits have a small number of operations that are repeated lots of times. So our circuits tend to be quite regular, at least for the protocols that the proofs are being used for so far. So we have multi-scalar multiplications and hash functions. So these are the main operations that we need in our recursive verification circuit. Excuse me. And we will also need to support application circuits. So in each step, we have a recursive verification, and we also need to prove something else. So in a blockchain example, we would need to prove that, say, a proof of work was valid or that transactions were valid. And so we're also going to describe this Pedersen-like hash function, which is called synsomia. And that's a good example because it shows how we can use lookups in a circuit. Okay, so how to do scalar multiplication. The curves that we're using are of this form, y squared equals x cubed plus b. So this is one idea for optimizing the scalar multiplication algorithm. So I don't know whether people are familiar with the double and adder algorithm for scalar multiplication. Are people familiar with that? In any case, the idea is that you keep an accumulator, you double it, and then you conditionally add the base point in each step. So you do that for each bit of the scalar. So there's a way of optimizing that, which is to just rewrite this as accumulator plus p, the base point, plus a. And that turns out to be more efficient because basically for each of these additions, you're computing a lambda value, which is the slope of a line between the 2 points. So you can compute the second lambda more efficiently because it's with the same a. And it turns out to be better to either add or subtract p rather than conditionally adding p. But we can do even better than that. So that gets us down to, the technique on this slide gets us down to 6 multiplications per scalar bit. But we can do better. So in Plonk, we can actually process 2 bits per row. So we used 6 constraints per bit in R1CS. And here we're processing 2 bits per row. So that's, it's 12 times fewer rows than we used R1CS constraints. So Jiwon Lee, you were asking earlier sort of whether in practice there was an increase in the number of constraints for Plonk circuits. but
Yes,
actually
exactly.
there's a quite
That's what I was curious
significant,
about.
yeah, there's a quite significant reduction in the number of constraints. So for these optimizations that you want to really heavily optimize, because you're using lots of them in a circuit.
Yes, it seems like.
Yeah. So in our verification circuit, we basically just need to multiply by some random scalar with 128 bits of entropy. So these are the U squared values from the inner product argument. And the idea is that we process 2 bits at a time. So we choose 128 random bits. And then we process 2 bits at a time, and we either subtract P, add P, subtract this endomorphism applied to P, or add the endomorphism applied to P. And so we're doing 2 curve additions for every 2 bits of our entropy. And the effect of this is to multiply. So the endomorphism phi here is equivalent to multiplying by this zeta value for some fixed zeta. So the whole algorithm here is equivalent to multiplying by zeta A plus B, where A and B depend on our vector of random bits, so our vector of 128 bits. So in order for this to be secure, we want the mapping from R to A and B, or from R to this effective scalar to be 1-to-1 so that we don't lose any entropy. So we do that in 2 stages. We show that from R to this tuple A comma B is 1-to-1, and then from that the effective scalar is 1-to-1. So I'm not going to go into all of the detail of this, but basically you can show that you can prove this first property provided that it's true for vectors of length 1 or 2. And then you can kind of show exhaustively that it's true for that length of vector. And then for the second part, so consider the smallest distance between 2 values of zeta A. With this A and B, we know that they're within a particular range. So starting at 0 and ending in this case at 2 to the 65 plus 2 to the 64. So if we consider all of the possible values of zeta A for A in this set, if the smallest gap between them is greater than this range, then we know that this mapping is 1-to-1. So basically, I wrote a program to to check this for any particular curve. So what it also generates a video while it's checking it. So what this is we're zooming in on the 0 value. So that's this red line. And here, this is the smallest distance. So here is, for example, 0 and zeta. And it turns out that when you go to these values zeta A to form this kind of lattice-like structure, and the smallest distance sort of reduces close to the origin. So if we run the video, what's happening here is it's zooming in on the origin, and then it can compute the this value, the smallest distance, and check that it's greater than this value. And it takes a while to run. So all of these lines are possible values of zeta A. So this is going to go down to about 2 to the 192 or so, which is much greater than 2 to the 65 plus 2 to the 64. So we know that this optimization works. Oh, it's actually 2 to the minus 186 roughly. So that this was the minimum distance that computed. So that works. So let's go on to some more optimizations. When we construct this proof system, we're using something called the Fiat-Shamir construction. So we start with an interactive protocol, and we replace the verifier with a hash function. So this is because we want non-interactive proofs. We want proofs that are just strings that anyone can verify. So that in the interactive protocol, so if we have the instance which is shared between the prover and verifier, the verifier sends a challenge, the prover sends part of the proof, verifier sends another challenge, and so on. And we want it not to be possible for the prover to cheat by knowing what the verifier's challenge will be. So for example, we don't want the prover to know C2, so to be able to influence C2 when it chooses pi1. So C2 should look random regardless of what pi1 is. So we do that by replacing the verifier with this particular kind of hash function, which is quite convenient for use in a circuit. So this is just addition in the field, and this is a permutation, which is efficient to compute in the circuit. And there are some optimizations that we can do. So for example, we can compress the values that we're inputting to F here. So these partial proofs, we can compress them to fewer field elements, but I'll just skip the details of that. And for the permutation, so we have several options. There have been quite a few proposals for hashes that are efficient in algebraic circuits recently. So two of the most promising ones are called Rescue and Poseidon. And this actually is why we needed this property of the fields, so that because both Rescue and Poseidon use these mappings that need to be permutations. But suppose that these are fairly new hashes, Rescue and Poseidon. So we might not be completely confident in their security yet, because symmetric cryptography is hard. And so this is actually the reason why in Sapling we used Pedersen hashes. So Pedersen hash only depends on the hardness of the discrete logarithm problem, but it only provides collision resistance. but that might be sufficient for some application level circuits. So actually what we're planning to do at ECC is we're planning to replace the sapling circuit, or to define a new version of the sapling circuit that uses Halo2. And it seems likely that we're going to use this a variation of Petersen hashes. But we want to define a version that makes use of all of the things that we can do in Plonk. So I'm going to explain what this looks like. The idea is basically we choose n random generators from the group, and we will be able to look up some bits of the message and look up one of these generators for each chunk of the message. So we can actually do that in just one row of Plonk. So this is the algorithm. We start with some random point, double it, sort of look up a base based on some message bits, add that, double it again, look up another base, and so on. And then so the result is a curve point, so it turns out to be sufficient to just take its x coordinate. And the reason we know this is secure, so we can consider it to be equivalent to a Petersen hash sort of turned on its side. So if these are the message chunks MI, we're processing 3 bits of the message at once here. So we have 7 bases on our table. So for this first message chunk, it has value 2. So we choose base 2. Second message chunk has 6. So we choose base 6, and so on. And it turns out that sort of ignoring Q, which is just a constant, we can read off the hash value by considering the columns in binary. So we read off this 0000001 as a binary value, and that is the scalar that we multiply base 0 by. So this is just equivalent to a normal Petersen hash, except that it's easier to compute because we're using we can do one lookup per row, so that we can process, in this case, 3 bits per row, but the size of the table that we use can be up to, say, 12 bits easily. So you can process 12 bits of the message at once. So I'm just going to skip this because this is basically showing the constraints in more detail. So this this first line of the loop, it's taking the next part of the message bits, and it's simultaneously constraining that to be within a given range. So suppose we're using a 12-bit table, we constrain that to be within 0 to 2 to the 12 minus 1. And it also looks up the point corresponding to those message bits. And then we do the elliptic curve arithmetic, so using the optimization that we said before, the A plus P plus A optimization. So how do we implement these lookups? First of all, do we have any other questions about the story so far? No questions? Okay, I'll just carry on then. We're nearly done. We've got just got a few more slides. I don't know how we're doing for time.
Is there any time limits?
Yeah, so I think we've had 1 hour 20. I don't really know how long we were supposed to take, but I think the whole event was 2 hours, so we're doing fine. Okay, so this is our relation that we want to look up, and it's often convenient to look up several field elements at once. So we're looking up W field elements here. So to do our lookup for synsomia, we form a relation on J with the X coordinate of the point and the Y coordinate of the point, such that this is our lookup. And then we can compress these 3 values into a single value just using a random challenge. So this is a very commonly used technique that we use in Plonk as well. So we've reduced the problem of doing a lookup into showing that this compressed value is in a table. So suppose that table has 2 to the k rows. By the way, this k happens to be the same as the k from earlier because our circuit has 2 to the k rows. Anyway, it could in general be different. And we have columns A and S. So we just add 2 new columns. And the goal is to enforce that every cell in this A column is equal to some cell in the S column. And that's sufficient to show that every cell in A is in the relation. In practice, we could have multiple columns here if we needed it. But we'll just describe the argument for 1 column. So how we're going to do this, we get the prover to supply a permutation of A and a permutation of S. And then every cell in this permutation of A either has the same value as the cell above it or the same value as the row in S. I'll show you what that looks like on a diagram in the next slide. And then the first values of A dash here and S dash are the same. So let's look at what, it's easier to see this in an example. Suppose we want to check that all of the A are in this set of the first 8 prime numbers. Okay, so that's our set S. And we can see that this is true for this example. So all of these are in the first 8 prime numbers, but they're in arbitrary order and there can be duplicates. So what we do, basically just sort this A column. But what's important here is that that like values are sorted together vertically. And then, so for each group of cells that are the same, we copy the first of them to S. So this, you can see that this satisfies the constraint that we had on the previous slide, because each value in A prime is either equal to the previous value or it's equal to the corresponding value of S prime. So, and we also have that the first 2 cells, so the topmost cells are the same. So by induction, we can show that all of the values in A prime must be in S. because if they're equal to the value in S prime, then that's obviously a value in S, or they're equal to another value in A prime that's earlier in the induction, so that also in S prime. And then notice that we've got some spaces here that aren't filled in. We need S prime to be a permutation, so we just fill those in with the sort of arbitrarily with the missing values. Okay, so that shows how the permutation argument, how the lookup argument works. And to actually check that these are permutations, so we do it in a very similar way to the main permutation argument that we use for copy constraints. So, so if we can actually prove these two permutations simultaneously using two different random challenges. So I'll skip the details of how to do that. But they're on this slide. So you can see that this looks very much like the earlier permutation argument, except that we're doing two things at once. And we're not specifying exactly what the permutation is because we're allowing the prover to choose it. Okay, any questions? Okay, I'll just give some credit. That's the end of the talk, but I'll just give some credits for people who have done work that Halo2 depends on. So it's joint work with, I should have said this at the beginning, I guess. Halo2 is joint work with Sean Bowe and Jack Grigg. These are the authors of Plonk and the authors of the papers on the inner product argument, and a bunch of people who have done theory in zero knowledge proof systems. Okay, so we'd like to thank all of those people. And that's it.
Okay, thank you, Daira and Intong. Is there any question? Actually, I have some question, Daira.
Yes, go
on. Regarding to this Halo2, actually you are using the blueproof style commitment schemes, right? In the Halo and Halo2. Yeah,
the inner product based. It's similar to bulletproofs. The thing that is different is if we go back to that slide, it takes a while to go back through the slides. This is a long presentation.
So anyway, my question is that did you think about the kate pairing commitment scheme also?
Yes. So to use the kate pairing, the kate commitment scheme, you need pairings, and because of the Kim Barbulescu attacks on pairings, you need the underlying elliptic curves to be of size around sort of 384 to 400 bits if they're using
which means
embedding degree of 12.
Yeah, MNT4 and MNT6, the cycles of elliptic curve, right? So still we have to use that like the elliptic curves for the kate pairing. Okay.
Yeah, so there are two options basically. You can use those MNT cycles, and then both of the curves will be pairing friendly. Excuse me. But then the curves need to be about 800 bits, I think. Yeah. So just because the target field needs to be large enough for the discrete log problem to be hard, and you have an embedding degree of 4, so the curves need to be larger. And the other option is to use what we call a half pairing cycle, which is a BN curve and another non-pairing friendly curve that form a cycle. So the first possibility using MNT curves is kind of what we were trying to avoid, sort of partly to simplify the cryptography by not needing pairings, partly to avoid trusted setup. There are some polynomial commit. There is at least one polynomial commitment scheme that uses pairings, but does not need a trusted setup, and that has square root proof size. But we just didn't consider the details of that so far. But that is a possibility to use that. I think we're concentrating on the case where we're using non-pairing curves and just depending on the discrete logarithm problem, because it's simpler and we want to avoid trusted setup.
Okay. Yeah. The performance-wise, do you think that the kate pairing style is better than that blip-proof style, or it will be same? What do you think about it? Proof size or the proving time? Ignoring about the process setup.
It is possible to combine pairings with Halo2. Yeah. It's just that that isn't an avenue that we've explored very much yet. I've had some thoughts about it. So that would allow you to do something like a shark, which is where you have an optimistic verification mode that uses pairings and is very fast and has very short proofs. And a more pessimistic verification that is basically just the discrete log based proof system. So that is attractive in some ways, but I think it turns out that despite the verification being linear, it is sort of reasonably efficient in practice. So Sean had a talk where he talks about benchmarks, and we think that for a roughly sapling equivalent circuit, it will be possible to do the full verification in, say, 300 milliseconds, something like that.
How much? 300 milliseconds?
Yeah. So it's not too bad. When you say that it's linear, then that sounds as though it's going to be impractical, but actually it's not.
300 milliseconds is quite good. Yeah.
Yeah. And you can also you can batch verify proofs, and also the fact that you have a recursive proof system, you need to verify fewer proofs in most applications, because you can just verify the proof at the end. You don't need to verify all the proofs that went into it.
Is anyone having any question?
Another thing that's worth saying in that context is that the verification is completely parallelizable. So it's actually quite hard to parallelize pairings after a certain point, because the algorithm is kind of linear. But that's not the case for this verification, because the hard part is just the multiscalar multiplication, and that's easy to parallelize.
About the Halo implementation, actually, we look at the GitHub.
Yes.
Actually, there's no documentation about how to use it, or.
So, it's early days. It's early days for that implementation.
So still, are you implementing or fixing, or?
It's so the recursion argument is not implemented yet.
Okay.
At the moment, we just have the so the underlying proof system, and that even that is not finished yet.
Okay.
But we'll let everyone know when it's ready for use, and we are intending to have a lot more documentation for it.
There is a question in the chatting. Do you have
I can't actually see the chat.
Yeah.
Can you read out the question?
I think we have to read the question for Dara. The question is, do you have an experimental result with any applications, like specific applications, some useful?
So we have a grant from the Ethereum Foundation to do some benchmarking and proof of concept circuits. So there should be some outputs from that soon, but I can't give you any.
So just
any
basically the
yet.
Ethereum blockchain.
So the grant is not specifically about the Ethereum blockchain. It's from the Ethereum Foundation, but it's we haven't specifically thought about how to use it with Ethereum. There are things that you could do with ZK rollups using Halo2 that would be very interesting on Ethereum. We just haven't implemented anything like that yet.
I mean, the first circuit we would want to write is the sapling circuit in Halo2.
That's right, yeah.
Yeah. And like Dara said, there's like so many possibilities you could, possible applications with Ethereum. Like ZK rollup, right now they have to publish one proof per transaction. Right, and then when someone challenges it, then that proof gets verified on chain. So if we can actually compress all the proofs in a batch into one recursive proof, then it doesn't have to be like optimistic anymore. It can just be one recursive proof per batch in a rollup. Yeah.
Yep.
Do we know that the timeline or schedule for the implementation of the Halo?
I mean, we should probably have something that's more usable in a few months. So part of our goal is we haven't committed to using this sapling on Halo2 in the next network upgrade after Canopy, but we want it to be sort of conceivable to do that. So that upgrade is scheduled for May 2021. So in order for us to potentially do that, then we'd have to have sort of an audited implementation of Halo2 and an implementation of the sapling on Halo2 circuits sort of somewhere in January. So that's a rough timeline, but don't quote me on that because things can change, schedules can slip, and it might not actually get into that upgrade at all.
Okay. Is there anyone? Maybe if we have a question, is it okay to send the email to you?
Yeah.
Is it okay? Yeah. So maybe during the studying of this Halo2, if we have a question, then we will ask a lot to you. Okay?
Yeah, that'd be great. Okay,
So
thank you very much.
Yeah, thank you so much for presentation and everything. Yeah. So see you next time, maybe.
I'll just. Yeah. I was just reading the chat, but it looks like I've already answered that question. So Okay, thank you very much.
Yeah.
Thank you.
Yeah, bye.
Thank you.
Thank
See you all.
Thank you.
Bye.
Thanks a lot.
Thank you.
마무리를 하겠습니다. 지금 좀